Hello, everyone. Welcome to this BPS in the month of October. So we'll have two talks today. The first one will be by Neeraja Sahastrabudhe from IISER Mohali. The second will be by Hari Narayanan from TIFR Mumbai. So first we have Neeraja, and she'll be talking about interacting urns on finite graphs. And so, Neeraja.
Thank you, Shikha. So, am I audible?
Yes, you are.
Yeah. Okay. So I would like to thank the organizers for inviting me to give this talk. I've been following Bangalore Pòlya-type seminar, and it's great to be talking here. All right, I'm just getting rid of things on the side. Okay. So I'm going to talk about interacting urns on finite graphs. So let me start by talking about what urn processes are, and then eventually get to what I mean by interacting urns. So I think anybody who has done even a basic course in probability has come across some sort of urn problem with balls in bins, a bag with balls of different colors, and then you try to compute probabilities of picking ball of a certain color and so on. These are some very basic undergrad questions that you come across in basic probability. So what I mean by urn models is exactly that. You have an urn or a bag or a bin with balls of different colors. And at every time you pick a ball and then you put back the same ball along with balls of other colors, or you remove some balls from the urn. So these are essentially what we call urn processes, and they fall under a large class of processes known as random processes with reinforcement, and find applications in various areas. So I would like to, right at the beginning, give this quote by Pòlya that I came across. So in 1957, apparently he said somewhere that any problem of probability appears comparable to a suitable problem about bags containing balls, and any random mass phenomenon appears as similar in certain essential respects to successive drawings of balls from a system of suitably combined bags. So this might be a bit of a stretch, but I thought it's a nice quote, given that I'm going to talk about urn processes. And indeed, traditionally, urn models have been used for modeling clinical trials, but over the years, they have found applications in study of various kind of phenomenon like opinion dynamics, disease spread on networks, evolutionary models, and more recently, even ant walks, so modeling ant walks. Okay, so let me start by classical urn model, which was introduced by Pòlya in 1923, so which is known as the Pòlya urn model. So you have an urn with finite number of balls of different colors. I'm going to restrict my talk to two-color urns. So we are going to look at urns with only two-color balls, let's say white and black. So you have an urn which contains non-zero number of white balls and non-zero number of black balls. And at every discrete time step, a ball is drawn from the urn uniformly at random, and it is replaced in the urn along with some A balls of same color. This A is fixed throughout. All right, so the famous theorem that they proved in 1923 says that the fraction of balls of white color converges to a random limit, which has beta distribution with parameters which are exactly the configuration of the initial configuration of the urn. So the limiting fraction depends on where you started from. All right, so over the years, various extensions of this model have been studied. So the popular ones being Friedman urn, for instance, being the most popular one. So in Friedman urn, the drawn ball is replaced in the urn with A balls of the same color and B balls of the other color. And in this case, the fraction of balls of white color converges to 1/2. So the nature of the limit changes drastically by changing the reinforcement process. So when you're adding balls of both color at every time step, the limiting fraction is 1/2. Is there a question? Okay. Then another generalization is Bakchi-Pal urn. So if you draw a ball of white color, you replace it in the urn with A balls of white color and B balls of black color. And if you draw a ball of black color, you replace it in the urn with C balls of black color and D balls of white color. And assuming that the urn is balanced, that is A plus B equals C plus D, then under certain condition, the fraction of balls of white color goes to C over B plus C, fraction of balls of black color will go to B over B plus C. Right. So by balanced, we mean that at every time step, you are adding, the total number of balls being added is same. So in Bakchi-Palan, you will either add A plus B balls or C plus D balls at every step. And by putting this condition, we are saying that the total number of balls being added at every step is same. Such replacement schemes or reinforcement schemes are called balance schemes. All right, so of course, these are some very old extensions of Pòlya models. Recently, multiple directions have been explored. So I have not given any specific references here, but if people are interested, they can get in touch with me and I can tell them specific papers. But I've just written names of people who have worked on these extensions because this is work across many papers. So multicolor urns and with reducible urn schemes, infinite color urns, and urns with random replacement. So for instance, here you could have A, B, C, D as random variables. So at every time step, you are adding a random number of balls in that case. Okay, so but I'm going to take a different direction of extension. I'm going to talk about interacting urn models. So what do I mean by interacting urns? So in these problems, I have more than one urn. So I have, let's say, n urns, such that reinforcement in each urn depends on all the urns in the system or on a non-trivial subset of the given urns. Again, we are going to restrict our discussion to two-color urns and balanced urn schemes. Okay, so let me define what I mean by a general two-color interacting urn model. So you have n urns with configuration WIT, BIT. By that I mean WIT is the number of white balls in ith urn at time t, and BIT is the number of black balls in ith urn at time t. Now, at time t, the reinforcement is just what you add. So I'm going to consider non-negative finite reinforcement, which means that at every time you add, you never take out any balls from the urn. You add balls or you leave it as such. So non-negative reinforcement and of course finite. So this reinforcement is essentially the difference between white balls in the urn at time t and t minus 1, and difference between black balls at time t and t minus 1. Okay. So this reinforcement in the ith urn depends on some urns in the system, let's say indexed by I1, I2 up to IKI. Then the conditional distribution. So what I mean is that the conditional distribution of this reinforcement, these random variables I, W, I, B, is determined by the configuration of these urns at I1, I2, IKI, and what is the number of white balls in it. So remember I said that I'm only going to talk about balanced urns. So it is enough to say what is the number of white balls in each urn, because my total number of balls that are being added to each urn is deterministic. So if I know how W's behave, I know how B's behave. Okay, so we call this set I1, I2, IKI, the dependency set of the ith urn. And in particular, if you are looking at graph-based interacting urn models, then a natural choice for dependency set is the neighborhood. So ith urn, the reinforcement in the ith urn will depend on the neighborhood of the ith urn, which is the kind of models I'm going to discuss. But before I get there, let me talk about what other people have looked at. So so there are these two papers on Pòlya interacting on models, where these authors, they consider n two-color urns, and the reinforcement is as follows. So in each urn at time 0, you have non-zero number of white balls and non-zero number of black balls. Now at time t plus 1, each urn with probability 1 minus alpha draws from itself, and with probability alpha, it draws from all the urns combined. So that is what it means when they say that a new white ball is replaced in the urn I with conditional probability alpha ZT plus 1 minus alpha ZIT. So this ZT here is, this is the overall fraction. So let me just maybe make that a bit more clear. So if I'm looking, if let's say I combine all the urns in the system, the fraction of white balls in that case would be sum over WIT divided by sum over total number of balls in the system. So this is summed over I. But because these are balanced urns, in fact, you are only adding one ball at a time. This TIT does not depend on I, it's same across urns. Because each urn, the initial conditions also are same. So each urn contains A white and B black balls at time 0. So this is then just sum over WIT divided by n times TT, which is exactly this. So reinforcement in each urn depends on all the urns combined, which in literature sometimes it is called the super urn, or on the urn itself. And this happens with probability alpha 1 minus. So a coin toss. Right. So what do they see in this system? So they prove the following. So they show that fraction of balls of white color, which is ZIT in every urn, converges almost surely to some random variable Z. And that is same as where the average is also going. So all the urns essentially are almost surely going to the same limit. And they also get the L2 rates of convergence, which is the second part. The rest of the results are about fluctuations of around the limit. So you look at the average, which is the ZT. So remember, ZT was the fraction of white balls in the super urn. So you look at ZT minus the limit, and when it is appropriately scaled, it converges to some Gaussian in distribution. And similarly, for each urn, you can get these scaling limits, except that the scaling depends on alpha in this case. All right. So, like I said, I'm going to talk about interacting urns on graphs. So,
yeah, hello, excuse me, I had a question.
Yes.
So the quantity alpha that you are talking about, it does not depend on the urn. It does not depend on
alpha
time.
Does not depend on me.
And it is deterministic, right? Throughout the process.
Yes.
Okay.
Yeah, but I mean, one can study nice phenomenon when you take, let's say, alpha depending on total number of urns, for example. Let's say if I take alpha to be some constant over capital N, which means if you go back here, so if you have larger number of urns, then you are less likely to look at the super urn. So you can then study some interesting phenomena there. Okay. So let me now talk about interacting urns on a finite directed graph. So this is joint work with Gushra and Kaur, who is in University of Virginia. So let me describe the setup. So you have a directed graph, V, comma, E. E is the set of directed edges. So we divide the vertex set of the graph into two disjoint sets. So one set we call stubborn vertices. These are the vertices with 0 in degree. And the other set we call flexible vertices. This is the vertices with non-zero in degree. So essentially, stubborn vertices will not get reinforced by any of the vertices in the graph. That's why they're called stubborn. Okay. And we exclude any isolated vertices. So we exclude these trivial cases where you have any isolated vertices because they will not reinforce anyone and they will not get reinforced by anyone. Similarly, we also exclude any vertices which have a single self loop. Because if you only have a single self loop, you're just doing self reinforcement independent of any other vertex in the in the graph, and these are then just single urns which have been studied. So we exclude these two. Okay. So now my vertex set is S union F, where S is the stubborn vertices, F is the flexible vertices, and I can just, without loss of any generality, I can assume that I can just label the flexible vertices from 1 to F. And I want to do that because I want to write my adjacency matrix in certain form. So with this labeling, my adjacency matrix looks like this. This is because there are no edges from flexible vertices to stubborn vertices, and there are no edges from stubborn vertices to stubborn vertices. So you have zeros on the right side.
Sorry, but you're
Now,
assuming the graph is connected, or because if the graph is disconnected, you might as well look at each individual component separately.
right. So actually, we do eventually, we'll decompose it into strongly connected components of F.
Yeah.
But you can also assume that it is strongly connected.
Yeah, okay. Thanks.
So the F part has to be strongly connected because stubborn vertices anyway will not have anything coming to them.
Right, right.
Yeah. Okay, so at each vertex, I place an urn which contains a certain number of white balls, certain number of black balls, non-zero number of white balls and black balls initially. And now I have to tell you how the reinforcement is done. So a ball is selected uniformly at random from all urns simultaneously and independently of every other urn. Now the balls are replaced into their respective urns, but their colors are noted. Now, if for every I, if the color of the ball selected from ith urn is white, alpha I white balls and mi minus alpha I black balls are added to all of its out neighbors. So maybe it's easier to see it this way. So this is the reinforcement matrix. So every urn I reinforces its out neighbors according to this matrix. Right? So if a white ball is picked from ith urn, it reinforces all its out neighbors with alpha I white balls and mi minus alpha I black balls. Similarly, when a black ball is picked, it reinforces according to the second row. So for every vertex I, the reinforcement matrix is different, but they are all balanced. Okay, so we are going to classify the type of reinforcement as follows. So if alpha I beta I equals mi, then we call it Pòlya-type. If it's not equal to mi, then we call it, okay. So alpha I plus beta I has to be strictly less than 2mi. So then we call it non-Pòlya-type. Of course, Ri also is not mi times I in case of non-Pòlya-type. I should have written that. Okay. So the question remains the same. What can we say about limiting fraction of balls of color white in each urn? Before I can tell you what happens, let me just get some notation out there. But if there's a lot of notation here, if you get confused, just stop me and ask me. So it doesn't matter if you work with alpha I beta I or alpha I over mi. I can just scale my matrix, reinforcement matrix. So I can use these interchangeably. Mi hat is the total number of balls being added to ith vertex. So this is the sum over mj, where j is in the in neighborhood. So ni is the in neighbors of I. So everything that is coming to I. And then I have these, so B is just the, it'll just come out, this sort of matrix just comes out in analysis. T is the total number of balls. So T1T is the total number of balls in ith urn at time T. So this is not same across urns anymore because it depends on the degree and what you're adding in every neighborhood. M is just the diagonal matrix with M1, M2, Mn, and M hat is the diagonal matrix of M1 hat, MF hat. Remember, nothing is being added to stubborn vertices. So the rest of the M hat, rest of the part after F is 0. And then we define this W matrix to be BMA M hat inverse. Again, this will simplify significantly if we do not consider vertex dependent reinforcement. If my Ri was same for all I, this W matrix will simplify significantly, as we will see. Okay, so now I can tell you what happens to the fraction of white balls in the urns. So there is a deterministic limit given by this, provided for every flexible vertex, there is a node V such that V leads to F, which means there is a connected path of directed edges from V to F. And V is either stubborn or the reinforcement at V is non-Pòlya-type. So as long as every vertex is receiving influence from a stubborn vertex or from a non-Pòlya-type vertex, the whole ZFT has a deterministic limit. So by ZFT, I mean Z1, Z2 up to ZF. Remember, stubborn vertices do not change. Their configuration remains the same. So I don't have to worry about that. I only have to worry about the first F coordinates of the vector Z. Okay. So once we know that there is a deterministic limit, we can also try to find out if there is synchronization, which means that is there a possibility that everything goes to the same limit. So this looks rather complicated, but I'll simplify it in a bit. So we have two synchronization conditions under which the urns will synchronize. So fraction of balls of white color in every urn goes to the same limit. And if you impose more conditions, for example, if the stubborn set is empty and so on, this limit simplifies. Okay, so what is this SC1 and SC2? What are these synchronization conditions? So the first one essentially says that, so if you look at this sum, so for every I, the sum over J in the neighborhood of I over the flexible vertices in the neighborhood of I, they essentially overall give you the same sort of reinforcement. So when you sum over these replacement matrices, the sum is independent of I. For every I, this is same, which makes sense. So if overall reinforcement that you are getting from all the flexible vertices is same at every urn, then everything should synchronize. Similarly, you get a very similar condition for stubborn vertices if the stubborn set is non-empty. Okay. So just to tell you what happens if the reinforcement is uniform across vertices, which means that Ri does not depend on I. So if your alpha I is alpha or Ai is A, Bi is B, Mi is M, then this matrix B, so this W matrix is nothing but, so let me just maybe go back to what M hat was. So remember, Mi hat is the sum of Mj. If this Mj does not depend on J, this is just M times the in degree. So instead of M hat inverse, you will get inverse of the degrees. Of course, in degrees, and in degrees of stubborn matrices, stubborn vertices is 0. So you have df inverse and then 0 everywhere else. So this A tilde is essentially adjacency matrix times the inverse of the degree matrix restricted to flexible vertices. And then synchronization conditions also reduce to something much simpler, and the limiting fraction also looks much simpler in terms of AB. Okay. So let me give you an idea of the proof of the convergence theorem. So for that, we use stochastic approximation theory. So very quickly, stochastic approximation scheme is a recursion like this. So X is in XT is in RD, and it satisfies a recursion like this, where the conditions are as follows. So H is Lipschitz. A, which are called ATs, which are called step sizes, are such that sum over AT is infinite and sum over AT square is finite. So diverging, but sum over AT square is finite. M is martingale difference sequence, which is square integrable and bounded in this way. The conditional expectation of the norm of MT is bounded. And of course, XT itself, supremum of XT is finite, almost surely. So if you have a recursion which looks like this and satisfies these conditions, so what stochastic approximation theory tells you is that XT will converge almost surely to stable limit points of the solutions of the ODE. Right? So this ODE. So X dot T equals H of XT. So stable solutions of this, which means one has to look at the Jacobian of H and see if there are any eigenvalues with positive real part.
Could you go back to the previous slide, please?
This one?
Yeah, thanks. So there's no condition on A to be non-negative or something?
Sorry, condition on A to be?
Non-negative or something?
Yeah, I mean, okay, that's it. It is a step size. So yes, it is positive. It is mostly done by T sort of thing, which we'll see very quickly. Okay. Okay, so the idea is to write down a stochastic approximation scheme for ZT and then see if H has the solution that we want and whether it is stable. Okay, so how do we do that? So I want to write a recursion for ZIT plus 1. So what is my ZIT plus 1? ZIT plus 1 is just the fraction of balls of white color at time T plus 1, which is WIT plus 1 over TIT plus 1. And this I can multiply and divide by TIT and get ZIT. So this part should be okay here. Now, my YI denotes the indicator of the event that a white ball is drawn from ith urn at time T. Right? So what I'm essentially doing is I'm writing WIT plus 1, sorry, I as WIT plus whatever you are going to add. Let me just call it IT plus 1, whatever you're going to add to the ith one. And what are you going to add? You're going to add alpha j many white balls and mj minus beta j many black balls, depending on what you draw. Right? And this is summed over the entire in neighborhood of I. Okay. All right. And now to make it a stochastic approximation scheme, so this part is just writing TIT as TIT plus 1 minus whatever you are going to add at time. Total number of balls, remember, you're just adding MI hat. So this part just comes from there. Here, I have just taken conditional expectation of this and subtracted. So I've added and subtracted conditional expectation. So this part here is just the Yj minus conditional expectation of Yj. Okay. And that makes, this is the martingale difference part. Okay. So this whole thing right here, so this part combines to give me my H function, and the rest is martingale difference part. So if you go back, that is exactly what I need. And yes, the step size is 1 over T. Remember, this number of balls, total number of balls in each urn is increasing linearly. Right? So this is exactly what I need for the step size. Okay. But I should get rid of this dependence on, I mean, this is, I can't say anything immediately from here. So I will write it as in the vector form. So in RF, so I can convert this. This is true for every urn I. I can write this in vector form, where now this becomes my martingale difference, and this gives me the H function. Right. And this is where the matrix W that I defined is coming from. Okay. So what about this step size? So remember that total number of balls, this TT, total number, this is the matrix of total number of balls. So on the diagonal, you have total number of balls in urn I, urn 1, urn 2, up to urn F. In fact, up to urn N, and then you have that is just equal to T0 plus T times M hat. M hat is the diagonal that is being added at every step. So this M hat F TF T inverse T is just 1 by T. It's like 1 by T. So that is exactly what you want for your step size. And your H comes out to be this. So now from the stochastic approximation theory, we get that this Z star is the unique equilibrium point whenever this matrix is invertible. And of course, it has to be stable. So we also have.
Sorry,
Yes.
Neeraja, I seem to have missed something. Is this the case when all the BIs are same?
No.
Okay, so then what is little b?
Little d, little b.
Huh.
Oh, okay. Let me
This is capital B, right?
no, so you have this vector of b's. So let me just write it. So B.
Yeah, I remember. Yeah, thanks. It's okay. I remember.
Okay. All right. So now the main part is to show that this I minus WF is invertible. And of course, the stability part comes very easy from the same proof. Okay. So here is where I would have to partition my F into strongly connected components. If one can avoid that by just taking strongly connected graph. So this WF part, then I can write as an upper triangular matrix such that on the diagonals, I have this I1 minus WF1. So this is my I minus WF. Right? So I1 is an identity matrix of appropriate dimension. I2 is an identity matrix of appropriate dimension, and so on. Okay. So once I do that, I only need to show that these matrices on the diagonal are invertible. And I do that by showing that each one of them is irreducible, which I know because of the strongly connected part, and substochastic. Okay. And the substochasticity part comes exactly from the condition that we had in the theorem. So we'll see how. So for any WF, the ijth element looks like this. So it is alpha I plus beta I minus mi. Indicator I is connected to J and divided by m hat J, which is just the sum of mi in the neighborhood of J. So this is just by definition of m. Okay. So now I want to look at column sums because I want to show substochasticity. So a column sum of any f prime. So f prime is, let's say, one of the strongly connected components. So if I take any f prime and I look at wf prime there, the column sums are essentially just sum of these, right? Okay. And by what I know, alpha I plus beta I minus mi is less than equal to mi. Okay. So what I got on here at the end is definitely less than equal to 1. I just have to show that it will be necessarily less than 1 for some column. But that is true because if you have, and so if you have something like this, so if you have a block of strongly connected, so let's say something like this. So there is a strongly connected component, but you have some stubborn vertex here, which is pointing to one of the vertices here. Right? So in that, so this thing in the denominator will be strictly larger than the numerator in that case. Right? If you don't have any such thing, then the other condition is that you must have a non-Pòlya type reinforcement. If you have a non-Pòlya type reinforcement, remember for that alpha I plus beta I minus mi is strictly less than mi. So right here in the numerator, you will get a strict inequality in that case. So in either case, this whole thing becomes strictly less than 1 for one of the columns. So that's the idea. As long as you have either non-polar reinforcement or a stubborn vertex eventually reinforcing this strongly connected component, you will have that at least one of the columns has strictly less than one sum, which makes this block substochastic. It is already irreducible and therefore it is invertible. And this happens for every block. So that is how we get that I minus WF is invertible. A very similar argument will also give you that, that if you look at this H function and then you look at the Jacobian of it, the eigenvalues have a negative real part. It comes with a it comes from a very similar invertibility kind of argument. Essentially the same argument. Okay. So we have got that we have this Z star that I showed you in the convergence theorem is the stable equilibrium. But now the question is, can we also get fluctuation limit theorems like they got for their simple system where there was no graph structure? And the answer is yes. So we assume the following in this case, just to make things simpler. Again, you can restrict to strongly connected components. So we assume that F is strongly connected. And additionally, we assume that this W matrix that we are getting is diagonalizable. So with these two conditions, we can get fluctuation theorems. So I have few other things that I should define. So because I have assumed that W is diagonalizable, I can diagonalize it using these matrices U and V with eigenvalues lambda 1, lambda 2, lambda n, which are such that real part of lambda 1 is greater than or equal to real part of lambda 2 and so on. And then I will just show you how fluctuation theorems look like because I won't have time to prove them. So this is what we get. So what is rho? Let me just tell you what rho is. So rho is the minimum eigenvalue of I minus WF. So the scaling depends on rho. Remember, okay, I'll come back to it. So scaling depends on rho. So when rho is greater than half, the scaling is square root of t. When rho is half, the scaling is t over log t. I have not put here what happens when scaling is less than half, but in that case, the limit is not Gaussian. There are very limited things known about that case. Okay, so these things also follow from fluctuation theorems of stochastic approximation scheme. And then you can look at some special cases. So you can look at what happens when W is symmetric. And these limits that I showed you, this limiting variance that I showed you, this simplifies significantly in that case. And now you can see clearly that this Z star minus 1 minus Z star comes out. And then, of course, this part which depends on the adjacency matrix. If you remember the earlier model that I showed you, where you look at the urn and the super urn, which is all the urns combined in the system, there also they had a dependence on Z minus 1 minus Z. So the limiting variance was, I'm sorry, yeah, limiting variance was some constant which depended on n. So some 1 by n sort of thing plus something and times Z into 1 minus Z. So here, obviously, we will get some dependence on the graph structure, which comes through from this matrix W. Then if you have synchronization, you can further write Z star as your limit point and you get something simpler. And if you have uniform reinforcement, you get something even nicer. Remember, when you have uniform reinforcement, this W matrix is nothing but some constant times your A tilde. So this A tilde is something like AD inverse. Right? Of course, you have to restrict to F. Okay. So in that case, you get further simplification and you get some very, so this, for example, for rho equal to half, you just get that it is some constant which depends on AB divided by N, and this J is nothing but a matrix of all ones. Okay. And I can also then talk about what happens for Friedman type Urn. So I can say this is a Friedman type Urn when A is equal to B. And in that case, the limiting point is exactly 1/2, which is what we expect. And the fluctuation part also simplifies significantly. Okay. So we have answered what happens to the fraction of balls of white color across Urns. We have answered about what happens to the fluctuations. Now the question is what happens. So I'll just skip that. It's just some detail. So now the question is what happens when, let's say there are no stubborn vertices and there exists V such that for all W that whose influence reaches to V, W is of Pòlya-type. So this is the case which we have left out from the convergence theorem, right? So what happens if you look at a strongly connected graph, if you have a strongly connected graph, there is no S, then S is empty, right? There are no stubborn vertices. So in a strongly connected graph, if every vertex is influencing according to Pòlya-type, what happens? We have not addressed that case so far. So in that case, I'm going to assume that the graph is strongly connected. And I'm going to assume that these balance conditions hold. And then I can say something about the about what happens to the fraction of white balls in each one. So the balance conditions are that 1 times MA is some constant R times 1, and MA1 transpose is some same constant R times 1 bar. So if you think of uniform reinforcement, this M is nothing but total number of balls being added times I. Right. So in case of uniform reinforcement, the first condition just boils down to saying that the graph is regular. In fact, it's regular in the sense that in degree of every vertex is same. Okay. And the second balance condition says that the initial total number of balls in each urn is same. This is just a technicality that I need for proof. Okay. So what can we say in this case? So I'm just removing this N and F now because I don't have to worry about the stubborn vertices. I have just this ZT, which is my vector Z1 up to Zn at time t. And in this case, under these balance conditions, we can say that there exists a finite random variable Z infinity such that ZT converges to Z infinity. So each ZTI, so by ZT converging to Z infinity 1, I mean that each ZIT converges to Z infinity. I'm not sure. Okay. What else can we say? We can also say something about, yes.
Can you go back to the go back 2 slides and just to show me what was the condition about W? Okay. Thank you.
Okay, and one can also get fluctuation limit theorems here with very similar scaling. So lambda 2 is the second largest eigenvalue of the matrix involved here. So the matrix that essentially the W matrix, but it'll look different here. It'll look, I mean, you only have to worry about A. Okay. So again, I'll not go into the proof of the fluctuation theorem, but I would like to sketch the proof of this part. So let me do that. So let's see what happens for Pòlya-type reinforcement. So remember we had that A equals B equals, so alpha equals beta equals M, right? Which means A equals B equals 1. So your capital B matrix just becomes identity. Your M hat is just this R constant that we defined times I, and therefore your W, this is what I was saying. So your W just becomes 1 over R MA. The other condition says that TIT is same as TJT for all IJ. So I can just drop that I and I just call it TT. Okay. So now what happens to the recursion of fraction of balls of color white? So this is still the vector. So zt plus 1 now is, so I'm just using the same recursion here. It just looks nicer because there is no dependence on I here. You have started with same number of total number of balls across urns, and you're adding the same number of balls. Okay. So I do the same technique essentially. So I add and subtract the conditional expectation of y. So that becomes delta yt plus 1. So this is yt plus 1 minus the conditional expectation of yt plus 1. And I've absorbed ma inside it because that's just a constant matrix. And then the rest of the part is this capital epsilon. Okay. So the first thing that is immediate is if I look at the average fraction, again, I can now define average fraction because the total number of balls across urns is same. So I can define 1 over n sum over zti. This is the average fraction of white balls. And this becomes a martingale with these conditions. So that is easy to see. So you have conditional expectation of z bar t plus 1, which is nothing but 1 over n zt plus 1 times this 1 transpose. You're just summing over zit. But from here, I know what is the conditional expectation. The conditional expectation of this second part is 0. This is the martingale difference. So the conditional expectation of zt plus 1 is just zt times this. And there is a 1 transpose. Now what happens when you multiply 1 transpose with this? Remember, your epsilon t is defined like this. And because of your balance conditions, this ma times 1 transpose is just r. So this whole thing vanishes. And then you are just left with 1. Identity times 1, which is 1. Which again gives you z bar t. So this z bar t is now a bounded martingale, and therefore it has an almost sure limit, which I call z infinity. And then I want to show that every other urn will also go to this limit z infinity. Okay. That is the part that remains. Okay. So for that, I want to look at the difference between zt and z bar t. This I can write as, so remember your z bar t is just zt times 1 transpose 1 by n. So I can write this difference as this zt times this matrix, which is I minus j over n. Okay, so now I want to show that I already know that my z bar t goes to this limit z infinity almost surely. If I show that this zt minus z bar t goes to 0 almost surely, I'm done. So I want to show that dt goes to 0. In fact, I can show that it goes to 0 in L2 and almost surely. And we do this by showing that the expectation of norm of dt goes to 0, and the norm also admits an almost sure limit. Okay. So this should have been t going to infinity. Okay, so we do this in 2 steps. So we show that the expectation of the norm goes to 0, and the norm admits an almost sure limit as t goes to infinity. Okay, so again, I'm going to look at this difference dt. So let me define a few matrices which will be helpful. And I'll also tell you why I needed all those conditions. So, sorry, this is just epsilon t. There is no t there. So this t is not there. Okay, so this now remember. So let me go back to the definition of this. So this is how it is. Now, if your adjacency matrix or W was diagonalizable, which is what we assume, so I can write that as just this. So this lambda, capital lambda matrix is just the diagonal lambda 1, lambda 2, lambda. So everything here is diagonalizable. This K, which is just this matrix, this is also diagonalizable. This is nothing but identity minus matrix of all ones divided by n. So this is also diagonalizable. So I can diagonalize both using these matrices P. And then I can just put that into the definition of dt. Okay. So my dt was this. Now my zt I know from here. So my zt is this. So I put everything and I diagonalize it, and I get that dt is nothing but sum over j from 0 to t, 1 over tj, uj, p inverse, and then you have these diagonal matrices inside. Now, if I look at the norm of dt and the expectation of that, this is exactly what dt is, right? I've just taken norm square and then taken expectation outside. If you take norm square, you get a tj square here. And the rest of it, of course, remains inside the norm. But then I can use some norm inequalities and so on and see that these things are just bounded above by something. What matters is this diagonal matrix. This diagonal matrix has lambda i's on the diagonal. Well, it is 1 minus r over tk, 1 minus lambda I. So essentially, it is governed by the eigenvalues of the adjacency matrix. Okay, so again, this is essentially 1 by 1, just bounding it by. So here I take maximum over I of all of these, and that is how I end up with the second largest eigenvalue. Remember, the first eigenvalue is 1, and that first part does not matter because you are multiplying by this matrix, which has first column and first row to be 0. So when you multiply the whole thing, the first element that you get is anyway 0. The rest of it decay to 0 according to this, which can further be simplified. So the expectation that you are looking at, so this is a sum of certain terms. The first term is exactly 0. The rest of them are decaying to 0. And from this, I can get exact rates of decay depending on lambda 2. So the lambda 2 that comes in here. So depending on lambda 2, these are the rates at which expectation of dt goes to 0. So these are all, so dt, remember, is the difference between zt and z bar t. So I have the rates of L2 decay to the limit. Okay, so I have shown the first part. I have shown that expectation of norm dt goes to 0. Now I have to show that norm dt admits an almost sure limit. For that, I look at conditional expectation of norm dt. So here, so let's look at the conditional expectation of norm dt plus 1 square. That I can write at the norm, I can just write as dt plus 1 transpose. And then here, I just add and subtract expectation of in each one of them. So if I add and subtract and then open up my expectation, like multiply everything and open up my expectation, I'll get 4 terms, out of which 2 terms will become 0. And I'll be left with these 2 terms, which is conditional expectation of dt plus 1 and the transpose of it, times this, which is delta is the difference. So delta is dt plus 1 minus this. Remember, when you add and subtract, you have this term and then you have this conditional expectation term, plus term as well. Okay. Now, conditional expectation of dt plus 1, I know what it is. It is dt times this matrix, which we have defined earlier. So this I can say because I know that conditional expectation of zt plus 1 given ft is zt times this. So now this part just becomes norm dt square minus this part. I'm of course using that these two commute. So what I wrote here, so expectation of dt plus 1 given ft is just expectation of zt plus 1 given ft times k, which is written on top here, which is zt times epsilon t. This we have seen. And then you have a k, but I can bring k on this side and make zt times k to be dt again, because k commutes with this epsilon t, which is exactly because of the balance conditions. Okay, so now I get that conditional expectation of norm of dt plus 1 square is dt plus is the norm of dt square minus this term here, and then you have the expectation of the difference. This part here, so if I just look at 1 minus this is positive semi-definite, and there is a minus in front, so I can get this inequality. It is easy to see it is positive semi-definite. It follows because this thing here inside it has this lambda matrix. So this is actually equal to 1 minus lambda t lambda transpose. If you diagonalize it, this is what you get. And the eigenvalues we know are less than or equal to 1. Because it's the scaled adjacency matrix, the eigenvalues of a scaled adjacency matrix. So this part is positive semi-definite, so I can get inequality like this. And then this part I can show is bounded above by a constant divided by t plus 1 square. Okay, so what have I shown? I've shown that the conditional expectation of dt plus 1 square, norm of dt plus 1 square is less than or equal to norm of dt square plus something which is where the sum of this is finite. And this is something what is known as almost super martingale. So I will just show you this very nice theorem of Robbins and Sigmund, which we use to show that norm, if norm dt satisfies this, then it has an almost shear limit. So the theorem is essentially this: you have some sequence of random variables ut, and then you have some sequences beta t, gamma t, which are also random sequences. Then if the conditional expectation of ut plus 1 given ft is less than or equal to 1 plus beta t times ut plus nu t minus gamma t. So we don't have all this, our beta t is 0. Then on the set where the sum of beta t is finite and sum of nu t is finite, ut converges almost surely to a random variable. So what we have in our case, beta t is 0, nu t is like 1 over t square. So sum of nu t is indeed finite for us, because this is what we have in place of nu t. So that gives me that the norm of dt has an almost shear limit. We have already shown that the expectation is going to 0, and therefore I get that dt is going to 0, and that gives me the convergence theorem for the Pòlya-type reinforcement. For the fluctuation theorems of Pòlya-type reinforcement, they are slightly more complicated, but you have to do essentially the same thing. So the first part is to show that z bar t minus zt when scaled appropriately converges to a Gaussian. And then you look at zt, which is your vector, minus z bar t times 1, and then show that when scaled appropriately, this also converges to a Gaussian. The only important point here is that for the first part, you only get root t scaling, whereas for the second part, because of all those matrices coming in, you get root t as well as root t over log t kind of scaling. So I think I'm out of time, right? So I'll stop here.
Okay, thank you, Neeraja.